throwing, catching, and propagating errors. In Swift, errors can be represented by values of types that conform to the error protocol. To throw an error, you use the throw keyword, followed by an error instance. The code defines an enumeration called vending machine error that conforms to the error protocol and represents possible errors that can be thrown by a vending machine. The vend function is marked with throws to indicate it can throw an error. Within the function, a guard statement checks for an out-of-stock condition and throws the corresponding error if the condition is met. There could be other logic for different conditions to throw the other defined errors. Defining error types. In Swift, you can define your own error types by conforming to the error protocol. This is typically done using an enum, as it's a convenient way to group related error conditions together. Each case of the enum can represent a different type of error that can occur within your program. In this code snippet, we define an enum named vending machine error that conforms to the error protocol, indicating that it can be used to represent errors in our program. The enum has 3 cases: invalid selection, insufficient funds, and out of stock. The insufficient funds case includes an associated value of type int, which can be used to specify the number of additional coins needed. This type of error handling allows you to communicate more detailed information about the nature of an error. Handling multiple errors. In Swift, you can handle multiple errors using do-catch blocks. Inside a do block, you can write error-prone code that may throw errors. Subsequent catch blocks can handle specific errors. You can have multiple catch blocks to handle different errors or conditions. Let's consider a scenario where a function may throw multiple types of errors. The code demonstrates handling multiple errors for a vend function that can throw errors from the vending machine error enum. When an error is thrown in the do block, the corresponding catch block catches and handles it based on the type of error. Each catch block is specific to a certain error case, customizing the error message for the user. If no specific catch block matches the error, a generic catch block at the end will catch and handle any unidentified errors. This ensures a robust error handling mechanism in your Swift application. Cleanup actions with defer. In Swift, defer blocks are used to execute a set of statements just before code execution leaves the current block of code, whether it leaves because an error was thrown or just because the block ends. In the provided code, open file name is used to open a file, and close file is used to close the file. The defer block ensures that close file is executed when the process file function exits, regardless of whether it exits normally or due to an error being thrown in the while loop. This ensures that the file is properly closed and the resources are released. Optional try. In Swift, error handling allows us to deal with errors in a controlled way. The try keyword is used to convert an error-throwing expression into an optional. If an error is thrown while evaluating the try, the value of the expression is nil. This is particularly useful when you are not interested in the details of the error and you just need to know whether the operation was successful or not. In the code example, canThrowAnError is a function that might throw an error. When we call this function, we do so with try. This means that result will be of type string, an optional string. If an error is thrown, result will be set to nil. Otherwise, it will contain the non-nil return value of the function. This is a concise way to handle errors without having to write several catch blocks if the specific error details are not important for our use case. Assertions and Preconditions. In Swift, assertions and preconditions are used to ensure that necessary conditions for the proper execution of a program are met. Assertions are checked only in debug builds and help catch developer mistakes during development. Preconditions are checked in both debug and release builds and are used to detect issues that can lead to system corruption or other disasters, enforcing critical conditions throughout execution. In the code example, we first declare a variable age with a value of -3, which is not a valid age. We then use an assertion to check if the age is greater than or equal to 0. If this assertion fails, as it would in this case, the program will crash in a debug build, providing a message indicating why the assertion failed. Later, we use a precondition to enforce the same check. Preconditions serve a similar purpose, but remain active in both debug and release builds, adding a layer of safety against incorrect values during the entire lifecycle of an application. Concurrency and multithreading. Concurrency in Swift allows multiple tasks to run simultaneously, potentially on different cores of a processor, improving the performance of the app. Swift concurrency uses async, await, and actors to handle concurrent operations safely. Multithreading, on the other hand, involves managing threads directly, which can be more complex and error-prone. Grand Central Dispatch, GCD, is a low-level API for managing concurrent operations in Swift that can simplify working with threads. The code snippet demonstrates a simple use of Grand Central Dispatch, GCD, for concurrency in Swift. It uses a global queue to perform a time-consuming operation, heavy computation, concurrently. Once the computation is complete, it dispatches a task on the main queue to update the user interface, update UI, with the result. It is essential to update the UI on the main thread because UI updates from background threads are not safe and can cause crashes or undefined behavior. Asynchronous programming with async await. Async await is a modern syntax introduced in Swift for handling asynchronous code. It allows developers to write asynchronous code in a way that looks synchronous, making it easier to read and maintain. In this model, functions can be marked as async, which means they can perform tasks that take time without blocking the main thread, and await is used to wait for these tasks to finish before moving on to the next line of code. In the provided code snippet, we have two functions that utilize async await. The fetch user data function is an async function that fetches user data from the internet. It uses await to pause execution until the data is fetched using URL session, which is an asynchronous network request. This stops the function from proceeding until the network request is completed without blocking the main thread. Once the data is retrieved, it's decoded into a user data object and returned. In update user interface, the await keyword is used again to wait for fetch user data to finish before proceeding to update the UI. This ensures the UI is not updated before the data is available. Higher order functions. Higher order functions are functions that can take other functions as arguments or return a function as a result. In Swift, these are common when working with collections. They include functions like map, filter, reduce, and more. Let's explore an example using map, which applies a given function to each element of a collection and returns a new collection with the results. In the code snippet, numbers is an array of integers. The map function takes a closure that squares each element. $0 refers to the current element in the iteration. The result is a new array squared numbers, containing each original element squared. No loop is needed. Map handles the iteration internally. Map, filter, reduce. The map function in Swift is used to transform an array. It executes a given function on each element in the array and returns a new array containing the transformed elements. In this code snippet, numbers is an array of integers. Squared numbers is a result of applying the map function to numbers. For each element in the numbers array, it is multiplied by itself, squared, and the result is stored in squared numbers. Custom operators. Swift allows you to define your own custom operators in addition to the standard operators. These can be useful for improving the readability and maintainability of your code when working with specific data types or performing complex operations. Swift provides different kinds of operators, such as infix, prefix, and postfix, which you can define based on your requirements. In the provided code, we define an infix operator *small, which is used to represent exponentiation, with the same precedence as multiplication for intuitive grouping in expressions. The *all operator is then implemented as a function that takes two double parameters, representing base and power, and returns the result of raising the base to the given power using the pow function. The operator is used to calculate 2 to the power of 3, which results in 8. Pattern matching. Pattern matching in Swift allows you to match against specific patterns of data and execute the appropriate code based on which pattern matches. It's commonly used with the switch statement, if case, and guard case, which provide powerful ways to handle multiple conditions and types. In the provided switch statement, some value is checked against different patterns. The first case 0 as int checks if some value is an int with a value of 0. The next case let some int as int matches any int and binds it to some int. The case is double checks for the type double. Case let array as int matches an array of ints. If none of the cases match, the default case is executed. This showcases Swift's ability to combine value and type patterns in a switch statement for powerful matching capabilities. Subscript syntax. Subscripts enable you to query instances of a type by writing one or more values in square brackets after the instance name. They are used to access information from collections, lists, or sequences. You can define subscripts on any custom class, structure, or enumeration. The syntax for defining subscripts involves the subscript keyword, parameters, and a return type. The following is an example of how to define and use subscripts. In this code, we define a struct named timesTable with a single subscript method. The subscript takes an int as a parameter and returns another int that is the result of multiplying the parameter with the multiplier property of the struct. When 3 times tabled 6 is called, it accesses the subscript method of the 3 times table instance, passing 6 as argument, and returns the product of 3, the multiplier, and 6, which is 18. Key path expressions. In Swift, key path expressions provide a way to refer to properties of a type in a decoupled and type-safe manner. They are particularly useful for querying and manipulating values on objects, and can be used with functions like map, filter, and reduce. In this example, person is a struct with properties name and age. A key path expression such as person.name provides a reference to the name property of a person instance. The map function is then used to iterate over the people array, accessing the name property of each person to create a new array called names. Similarly, person.age is used to create an ages array containing the ages of each person in the people array. The backslash before person indicates that a key path expression follows. Property observers. Property observers in Swift allow you to run code before or after a property changes. The willSet block runs before the property changes, and the didSet block runs after the property has changed. They provide a way to monitor and respond to changes in a property's value. In this code, a player class has a score property with observers. The willSet observer is provided with new score, representing the new value. Before the score changes, it prints a message. The didSet observer uses old value, the property's previous value, automatically provided by Swift. After the score is updated, it calculates the difference and prints a message if the score increased. When we instantiate a player object and then set its score to 10, both observers are called, printing messages before and after score is updated. Lazy stored properties. Lazy stored properties in Swift are properties whose initial value is not calculated until the first time they are used. They are useful when the initial value for a property is computationally expensive to provide and might not be needed during the lifetime of the object. In the code snippet, expensive class represents a class that is costly to instantiate. My class has a lazy stored property called expensive object. When an instance of my class is created, expensive class is not initialized until expensive object is accessed for the first time. The comment in the code indicates when the expensive class initializer is actually called. Introduction to SwiftUI. SwiftUI is a modern framework for building user interfaces across all Apple platforms with the power of Swift. It provides a declarative syntax that allows you to design and develop your app in a simple, straightforward manner. This code defines a basic SwiftUI view called Content View. It imports the SwiftUI framework and declares a struct conforming to the view protocol. The body property, which is required for all views, returns some view. Here, it's a text view that presents the string Hello SwiftUI. The content view previews struct conforms to preview provider, and it's used by Xcode to render previews of the SwiftUI views in the canvas. Building user interfaces with SwiftUI. SwiftUI is a declarative framework for building user interfaces on Apple platforms. It uses a straightforward syntax to create views. Let's start by creating a basic structure of a SwiftUI view, which represents a simple screen with text. In the given code, we import the SwiftUI framework, then define a content view struct that conforms to the view protocol, indicating that it represents a view in the user interface. The body property is required for all views and defines the view's content. Here, it contains a text view displaying the string Hello SwiftUI. The content view previews struct conforms to preview provider, which is a protocol used by Xcode to render previews in the canvas. State and data flow. In SwiftUI, @state is a property wrapper that you use to declare state for local data that your view depends on. When @state property changes, the view invalidates its appearance and recomputes the body. This code defines a content view struct that conforms to the view protocol. Inside, we declare a state variable counter initialized to 0. @state allows the variable to be mutable inside the struct, which is usually immutable. The view shows a text that displays the counter value and a button. When the button is tapped, it increments the counter. Since counter is observed by the view, each increment will cause the view to update and display the new value. Binding. In SwiftUI, a binding is a connection between a UI component and an underlying piece of state. It allows for two-way communication, meaning that when the state changes, the UI updates accordingly, and when the user interacts with the UI, the state is updated. This is useful for controls like sliders, text fields, and toggle switches that need to both display and modify values. In the code example, we declare a struct named content_view that conforms to the view protocol. Inside it, we define a state variable, username, which is marked with @state to indicate it holds mutable state. The text field element is created with a placeholder and a binding to the username state variable. The $symbol before username is the syntax to create a binding. As the user types into the text field, username is updated, and if username is programmatically changed, the text field's displayed text will update as well. SwiftUI views and controls. In SwiftUI, text is a basic view that displays read-only text on the screen. It's similar to UI label in UIKit. You can style the text with modifiers, and it automatically wraps within the containing view. This code creates a text view with the string Hello SwiftUI. With modifiers, the font is set to the built-in title style, the font weight is set to .bold, and the text color is set to blue. These modifiers chain to the text view, each modifying the view's appearance. Navigation and modal presentations. Navigation in SwiftUI is commonly handled using the navigation view and navigation link components. Navigation view acts as a container for the views that support navigation, and navigation link is used to create the user interface for navigating between views. Here's a simple example demonstrating their usage. Animations and gestures. In SwiftUI, you can add animations to your views using simple modifiers. Implicit animations are animations that automatically run when a view's state changes. Let's add an implicit animation to a view that changes size when tapped. This code defines a content view struct conforming to the view protocol. It contains a @state variable, isScaled, which determines the scale effect of a circle. When the circle is tapped, the onTap gesture modifier triggers an animation block using withAnimation. The call to toggle on isScaled inside this block causes SwiftUI to animate the scaling of the circle from its initial size, 1.0, to 1.5 times its size. Integrating with UIKit. SwiftUI provides a way to integrate UIKit components through the UI View Representable protocol. It lets you wrap a UI View-based component for use in SwiftUI. This example shows how to create a SwiftUI view that integrates a simple UIKit UI label. In the code, UI label representable conforms to the UI View Representable protocol and provides two mandatory methods: make UI View and update UI View. Make UI View is called to create the UI label, and Update UI View is called to update it with the latest data, in this case, the text property. In Content View, the UI label representable is initialized with a string and can be used like any other SwiftUI view. Accessibility. In SwiftUI, accessibility features help make your app usable by everyone. The accessibility modifiers allow you to customize the way your UI is presented to assistive technologies like VoiceOver. In this code snippet, we have a text view that displays the text profile photo. We've added two accessibility modifiers to this view, accessibility label and accessibility hint. The accessibility label modifier is used to define a label that VoiceOver will read instead of the text itself, in this case, user profile photo. The accessibility hint provides additional context about what will happen if the user interacts with the control, here indicating that double tapping will open the profile photo. SwiftUI Lifecycle. The SwiftUI Lifecycle refers to the sequence of events that an app goes through from startup to termination. At its core, SwiftUI Lifecycle management revolves around the app protocol for the application as a whole and the scene protocol for each of the app's scenes. The code defines an app entry point using @main. My app conforms to the app protocol, which requires a body property returning some scene. Inside, a window group is used to create a new scene that will contain the content view. The lifecycle events, such as application did finish launching, application will enter foreground, and application did enter background, are handled by SwiftUI without the need for explicit implementation in most cases. This is the starting point for a SwiftUI app's lifecycle.